Welcome, dear listener. I'm Tina, scientist and lifelong terrible sleeper. I made AI for sleep to help ease my own restless nights after I learned a busy mind tends to drift off when it's gently occupied, not forced quiet. So everything here is built to give your thoughts somewhere soft to land. Settle in, dear friend, and let yourself sink into this quiet moment by the fire. Tonight, we're going to explore something remarkable that's happening right under our noses, in the machines that sit beneath our desks and rest quietly on our nightstands. The world of artificial intelligence is shifting, and those powerful digital minds we've grown accustomed to reaching for in distant clouds are beginning to find their way home. Personal AI agents, the kind that can truly understand and assist with your daily work, are no longer confined to someone else's servers. They're learning to live and think right there beside you, on your own device, private and powerful. Let's begin by discovering how this quiet revolution is taking shape, starting with a vision that's rapidly becoming reality. But first, a gentle observation. Most of the people who drift off to this channel have never actually hit subscribe. So if I've ever helped you in any way, you can return the favor with a simple and free action that will encourage me to keep going. Now, without further ado, let's fall asleep. Picture your computer as a helpful assistant that sits quietly in the corner, watching how you work, learning your patterns, and eventually stepping in to handle the tedious parts of your day. That vision of personal AI agents is rapidly moving from science fiction to reality, and NVIDIA just unveiled a significant leap forward in making these digital teammates both powerful and private. At NVIDIA's GTC event in Taipei, the company introduced RTX Spark, a new class of Windows PCs designed specifically for running AI agents locally on your device. Think of it like the difference between having a brilliant consultant who works in your office versus one who operates from a distant headquarters, where every conversation has to travel through uncertain channels, and you never quite know who else might be listening in. The hardware specifications tell a compelling story about what these agents actually need to run effectively. RTX Spark delivers up to 1 petaflop of AI compute power paired with 128 gigabytes of unified memory, creating a foundation robust enough to handle the computational demands of sophisticated on-device agents without breaking a sweat. This represents a fundamental shift in how we think about the relationship between humans and computers, moving from the traditional tool and user dynamic to something more like a partnership. Imagine transitioning from owning a well-crafted hammer to working alongside a skilled carpenter who understands your projects, anticipates your needs, and can execute complex tasks while you focus on the creative and strategic elements. The privacy and security implications drive much of this local-first approach. NVIDIA has partnered with Microsoft to create new Windows security primitives specifically designed for agent operations, providing what you might think of as a sophisticated set of locks, keys, and security protocols that ensure your digital assistant operates within carefully defined boundaries. The NVIDIA OpenShell runtime builds on these security foundations, offering developers an easy-to-deploy package that handles the complex orchestration of secure, on-device agents. Popular projects like Hermes Agent and OpenClaw are already integrating these security primitives into their Windows applications, creating a more trustworthy ecosystem for agent deployment. Performance optimizations accompany these security enhancements, particularly in the realm of inference speed. NVIDIA collaborated with the llama.cpp community to implement multi-token prediction, a technique that works like having a thoughtful conversation partner who can anticipate and prepare several likely responses while you're still speaking, rather than waiting for each complete thought before beginning to formulate a reply. These optimizations deliver impressive real-world improvements, with 2x performance gains on Qwen 3.6 and 3.5 27B models, and 1.6x performance boosts on the larger 35B variants. For AI enthusiasts running multi-GPU configurations, the improvements become even more pronounced, with tensor parallelism enabling up to 2x memory efficiency and 1.8x compute improvements when using two equivalent GPUs. The collaboration extends beyond pure inference optimization into the realm of practical agent capabilities. NVIDIA is working with H Company to develop computer use tools that allow agents to navigate a PC by literally seeing the screen and operating mouse and keyboard inputs, much like a careful observer who watches over your shoulder, learns your patterns, and can eventually replicate your actions across any application, even those without formal APIs. This computer use harness represents a particularly elegant solution to the integration challenge that has historically limited agent adoption. Rather than requiring every application to expose specific interfaces for agent interaction, the system works at the visual and input level, creating a universal compatibility layer that treats the desktop environment like a human would experience it. H Company's Holo computer use models have been optimized specifically for NVIDIA GPUs, delivering 2x speedup improvements while reducing memory consumption by 35%. These models are available for download now, with the Holo desktop application expected to arrive soon for RTX and DGX systems. For developers who prefer Linux environments, NVIDIA DGX Spark provides the most capable personal agent platform, combining large memory configurations with fast compute and full compatibility with the NVIDIA CUDA ecosystem. Think of it as the difference between a well-equipped workshop and a full industrial facility, both serving similar purposes, but offering dramatically different scales of capability. The DGX Spark OS release includes streamlined Nemotron installers and automatic sandboxing capabilities, making agent deployment significantly more straightforward than previous generations. Nemotron now runs across the full spectrum of NVIDIA RTX and DGX systems, both on native Linux and through Windows Subsystem for Linux. Collaboration with VLLM has yielded additional performance improvements specifically for agent workloads. New optimized NVFP4 checkpoints for Qwen 3.635B deliver 2.6x performance improvements on DGX Spark compared to previously available checkpoints, incorporating kernel improvements, mixed precision support, and CUDA graph optimization for multi-token prediction. The creative applications showcase perhaps the most immediately tangible benefits of this agent-focused hardware approach. NVIDIA's partnership with Adobe involves re-architecting both Premiere and Photoshop specifically for RTX Spark, creating what you might imagine as the difference between using professional tools in a cramped garage versus a purpose-built studio with unlimited power and space. Adobe Premiere will feature a completely new video pipeline that leverages RTX Spark's unified memory architecture, Blackwell GPU capabilities, and TensorRT software stack. This integration promises real-time performance for editing and color correction, along with more efficient rendering of complex timelines that would previously require significant waiting periods. The next-generation Photoshop engine focuses on GPU-accelerated compositing, enabling live filters, high dynamic range processing, and modern natural brushing experiences. Rather than treating GPU acceleration as an afterthought, this AI-native pipeline harnesses the full computational power available in RTX Spark from the ground up. Perhaps most intriguingly, Adobe plans to extend both Premiere and Photoshop to work collaboratively with Windows agents, creating what amounts to a digital creative partner that can assist with complex workflows. Imagine having a skilled assistant who not only understands your creative tools, but can anticipate your needs, suggest optimizations, and handle repetitive tasks while you focus on the artistic vision. NVIDIA Broadcast 2.2 represents another step forward in creator-focused improvements, graduating the studio voice feature from beta status. This AI-powered audio enhancement makes any microphone sound studio quality, now running on GeForce RTX 3060 GPUs and above, with improved performance characteristics. The integration of Elgato Stream Deck support across both NVIDIA Broadcast and Project G Assist creates new possibilities for streamlined content creation workflows. Think of it like having a sophisticated control panel where complex AI operations become as simple as pressing a single button, removing the friction that often separates creative ideas from their technical implementation. Blender Cycles will integrate DLSS 4.5 ray reconstruction as a new denoising option, transforming the path tracing viewport into an interactive, real-time experience. This allows 3D artists to navigate through scenes while seeing near final render quality, fundamentally changing how lighting and look development work gets done. RTX Video Frame Generation introduces another practical AI enhancement, doubling or quadrupling video frame rates in real time. This addresses a common pain point, where AI models typically generate video at 15 to 20 frames per second, requiring post-processing to achieve smooth playback. Instead, creators can work at comfortable generation speeds and let the system interpolate to professional frame rates automatically. The broader ecosystem improvements extend to pre-installed capabilities on creator hardware. Asus ProArt laptops now ship with Black Forest Labs Flux 2 Klein 4B image model pre-installed through the MuseTree application, optimized with NVFP4 format and TensorRT. This creates an unboxing experience where users can generate images locally immediately without model downloads or complex setup procedures. These optimizations deliver up to 2.5x speedup improvements and 560% memory reduction compared to standard implementations, demonstrating how purpose-built integration can dramatically improve the user experience. It's like the difference between assembling a complex machine from scattered parts versus receiving a finely tuned instrument that works perfectly from the moment you first use it. The NVIDIA AI for Media SDK introduces additional capabilities, including new lip-sync NIM microservices optimized for French, German, and Spanish, along with active speaker detection services that support multi-camera configurations with cross-video speaker correlation. These tools represent the kind of specialized professional-grade capabilities that become accessible when sufficient computational power runs locally, rather than depending on cloud services. As we settle into sleep, consider how this convergence of powerful local hardware, sophisticated security frameworks, and optimized software represents more than just incremental improvement. We're witnessing the emergence of a new category of computing device, one designed not just to execute our commands, but to understand our workflows, anticipate our needs, and collaborate with us in ways that feel natural and trustworthy, all while keeping our data and processes securely under our own control. You've just heard about NVIDIA's vision of personal AI assistants and their new RTX Spark computers, designed to bring powerful agents directly to your desktop. Take a gentle breath and let that possibility settle with you. The idea of having such capable help that never needs to leave your side or share your conversations with distant servers. You don't need to remember every technical detail, just the warmth of knowing that this kind of personal assistance is becoming real. Now, let's explore what makes this possible, how these agents actually come to life on your own machine, and why more and more people are choosing to keep their digital helpers close to home. Picture opening a brand new laptop, but instead of installing software for hours, you're running sophisticated AI agents in minutes, and these agents never need to phone home to the cloud. The rise of autonomous, long-running AI agents has introduced a fascinating new class of compute demand: tasks that maintain large context windows, spawn concurrent subagents, and iterate continuously without any cloud dependency. Security and privacy concerns are accelerating this shift toward local agents, where developers can keep sensitive context on their own hardware, retain direct control over what an agent can access, and eliminate those nagging per-token costs that add up with cloud services.
Think of NVIDIA DGX Spark as a specialized workbench designed specifically for building and running autonomous agents locally, much like how a jeweler's bench has all the right tools and lighting positioned exactly where they're needed. At Computex 2026, NVIDIA made it significantly easier to get there, introducing a streamlined path from unboxing to running AI agents in minutes, excluding only the initial model download, which depends on your network speed. There are also substantial model performance improvements with Qwen 3.6 and a guided multi-node cluster setup for teams that need to scale beyond a single device. NVIDIA Nemotron orchestrates this entire execution environment, functioning like a master conductor who coordinates the orchestra of models, runtimes, and security layers. By running autonomous agents on hardware they own, with Nemotron managing the show, developers can keep sensitive context on device, maintain direct control over agent access permissions, and step away from the subscription treadmill of cloud-based inference costs. Getting a local AI agent running has historically been like assembling furniture without instructions, involving sourcing the right model, configuring an inference backend, installing a runtime, and somehow wiring them all together. That process could consume the better part of a day, even for experienced developers, with plenty of opportunities for things to go sideways. The new streamlined Nemotron installation path changes that fundamental experience, compressing what used to be a day-long adventure into something you can accomplish over coffee. For new systems, the experience begins with unboxing and first-time setup of DGX Spark, and the latest version of the system software, the June 2026 release, delivers the most streamlined out-of-box experience yet. With this release, over-the-air updates are no longer installed by default during initial setup, reducing setup time and getting users to the Ubuntu desktop sooner, like skipping the lengthy software updates that usually greet you on a new phone. Nemotron is an open-source blueprint that packages 3 essential components into a single install, much like a Swiss Army knife that combines multiple tools in one compact form factor. It bundles open models, an agent harness like Hermes Agent or OpenClaw, and the NVIDIA OpenShell runtime into a cohesive unit that just works together. OpenShell deserves special attention as a secure, sandboxed execution environment designed specifically for running autonomous agents more safely, functioning like a protective greenhouse that lets your plants grow while shielding them from harsh weather. It adds access controls, privacy protections, and operational guardrails to the agent loop, creating boundaries that keep things contained. Combined with on-device inference, this gives developers a much stronger default security and privacy posture for agentic workloads. The installation process starts after completing the out-of-box experience, when DGX Spark reboots and opens build.nvidia.com/spark, with the Nemotron playbook prominently displayed for a guided walkthrough. The entire installation reduces to running a single command that handles everything, like having a master key that unlocks all the doors you need to pass through. That magic command downloads and executes a script that installs Node.js if needed, installs OpenShell, clones the latest stable Nemotron release, builds the command line interface, and runs an onboard wizard to create your sandbox. The installation wizard walks you through a few simple decisions, accepting the Nemotron and OpenClaw licenses, confirming an express install, and automatically setting up local Ollama with Qwen 3.6-35B downloaded and ready to go.
Once the install completes, accessing your agent feels like opening the door to a workshop where everything is already organized and ready for use. You generate a gateway token with a simple command, then open the tokenized URL in a browser, being careful to use the exact IP address 127.0.0.1 rather than localhost, since the gateway origin check requires that specific format for security reasons. A quick test message, something simple like hello or what can you do, confirms that the full stack is operational and responding correctly. The local Olama model is already selected and configured automatically during onboarding, so there's no hunting through menus or debugging connection issues. Just immediate responsiveness from your local inference engine. With your sandbox running smoothly, the Nemotron Applications Playbook offers 4 ready-to-run agents to get started, each one like a different specialized assistant with its own area of expertise. The Daily Personal News Digest acts as a scheduled morning briefing service that sweeps your topics and posts a structured digest to Telegram, keeping you informed without the noise. The Software Development Agent functions like a tireless coding partner that reads a local project directory, builds a comprehensive plan, writes and reviews its own code, all with no outbound network traffic beyond local inference. This agent can work entirely offline once the models are downloaded, making it perfect for sensitive development work or air-gapped environments. The Deck and Document Reviewer operates like a meticulous editor with a security mindset, red-teaming files before they go out and returning a severity-ranked punch list of inconsistencies, unsourced claims, and accessibility issues. It's the kind of thorough review that catches embarrassing mistakes before they reach important audiences. The Calendar Negotiator serves as a scheduling chief of staff, transforming those endless "when can we meet" email threads into confirmed calendar events, like having a diplomatic assistant who speaks the language of everyone's availability and somehow finds the magic time slot that works for all parties involved. Customizing agent behavior happens through several key levers, starting with the system prompt, which you can edit from the dashboard to shape how the agent responds and what it should ask before taking action. More specific prompts produce more reliable agents, like giving clearer directions to someone helping you navigate. The more precise your instructions, the more likely they are to take you exactly where you want to go. Tool permissions work through OpenShell network policies that control which external destinations the agent can call, functioning like a carefully designed fence that keeps your dog safe in the yard, while still giving them room to run and explore. Narrower permissions reduce unexpected behavior, creating predictable boundaries that prevent agents from wandering into territory you didn't intend them to access. Integration capabilities mean that if you enabled a messaging channel during onboarding, the agent is already reachable there, so you can send it a message from your phone and watch it respond using the same local model. This creates a seamless bridge between the sophisticated local inference and your everyday communication tools. Developers can dive deeper by swapping in different models, adjusting OpenShell permissions, and connecting agents to local workflows, like rearranging the tools in a workshop to better suit a particular project. To spin up a new sandbox with a different model, you run the onboard command with specific flags, though the fresh flag destroys and recreates the existing sandbox, so you'll want to use a different name parameter to create additional sandboxes without affecting existing ones. The wise approach is to start narrow, giving the agent a single well-scoped task on your first run, something manageable like summarizing a file or answering questions from a local document. Verify that the response and tool calls look right before expanding permissions, like testing a new recipe with a small batch before cooking for a dinner party. Several commands
become invaluable as you iterate and refine your agents. Tools that let you peek under the hood and understand what's happening. The status command shows sandbox health and inference status. The logs command with the follow flag streams real-time activity, and the list command shows all registered sandboxes, giving you a complete picture of your local agent ecosystem. Performance improvements with Qwen 3.635B on DGX Spark deliver up to 2.6 times faster inference compared to previous configurations, like upgrading from a winding mountain road to a straight highway that gets you to your destination much more efficiently. These gains come from NVIDIA's NVFP4 quantized checkpoint using MTP optimizations, along with additional improvements to VLLM CUDA graph support for MTP with FlashInfer, BF16 auto-tuning across FlashInfer MoE kernels, and optimizations in TinyGem and cuBLAS BF16 paths. For developers who need more memory or throughput than a single DGX Spark can provide, clustering multiple units creates a high-bandwidth supercomputer that's like connecting several powerful engines to pull a much heavier load. The Cluster Assistant in NVIDIA Sync automates the complex process of connecting 2 to 4 DGX Spark units, handling the networking configuration that would otherwise require deep expertise in high-performance computing. Clustering matters significantly at the model level, where 2 DGX Spark nodes provide 256 gigabytes of unified memory, sufficient for roughly 400 billion parameter models, and 4 nodes provide 512 gigabytes. That's enough computational space to run large mixture of experts models, multi-agent pipelines with multiple concurrent inference instances, or fine-tuning jobs that benefit from distributed memory, like having a library with enough shelf space for the largest reference collections. Setting up the cluster requires configuring the ConnectX-7 networking, since each DGX Spark has ConnectX-7 NICs that support 200 gigabits per second RoCE, but using them correctly involves configuring NetPlan, setting up node-to-node SSH trust, verifying bandwidth across each link, and knowing the right IP assignment scheme for the target topology. The Cluster Assistant simplifies this network configuration through a guided workflow inside Sync, like having an expert electrician wire your house instead of trying to figure out the electrical code yourself. Starting from devices already enrolled in Sync, the Cluster Assistant walks through system readiness checks including OTA version and sudo access, ConnectX-7 topology detection using probes that run on each node in parallel, IP planning and deconfliction with NetPlan application, and bandwidth validation using specialized tools. It also handles inter-node SSH setup using keys routed over the ConnectX-7 fabric, creating secure communication channels between the clustered nodes. Supported physical configurations include 2-node direct connection with a single QSFP cable and no switch, 3-node ring topology using 3 QSFP cables with both ConnectX-7 ports active per node, and 2 to 4 nodes via a QSFP switch, each configuration like a different way of arranging desks in an office to optimize collaboration and communication flow. The switch requirements specify minimum 4 ports QSFP56DD, breakout support to various speeds, recommended maximum port speed of 200 to 400 gigabits per port, and RoCE v2 support with substantial switching capacity. These updates at Computex 2026 address the 2 biggest blockers to building production-quality local agents: time to first agent and access to the compute needed to run large models, like removing both the steep learning curve and the hardware barrier that previously kept this technology accessible only to specialists. The streamlined NemoClaw install gets developers from unboxing to a running OpenClaw agent with Qwen 3.6-35B as the default model and a built-in secure execution environment. For teams that need more computational power, the Cluster Assistant in Sync removes the expertise barrier to spinning up a multi-node cluster with full ConnectX-7 performance, democratizing access to the kind of distributed computing that can handle the largest models and most demanding agentic workloads. It's like having a bridge that connects you to capabilities that were previously on the other side of a technical chasm, now accessible with guided assistance, rather than requiring years of specialized knowledge.
We've just walked through the practical reality of running AI agents locally, seeing how NVIDIA DGX Spark makes it possible to go from opening a laptop to running sophisticated agents in minutes. Rest easy knowing that these technical advances are making personal AI assistants more accessible than ever before. The beautiful part is how natural it all feels once it's working. Now, let's step into the world where this vision is already alive, where AI agents are quietly helping people with their daily tasks, and see how major companies are working together to make building these helpers even easier for the developers who create them. Picture a bustling office where every desk has its own personal assistant, quietly working alongside each employee, helping with coding, editing videos, managing files, and handling the countless small tasks that fill a workday. This is the world of AI agents, and it's already here, transforming how we interact with our personal computers in ways that feel both futuristic and surprisingly natural. NVIDIA and Microsoft have joined forces to make building these on-device agents much simpler for developers working on Windows, bringing together easier setup processes, built-in security measures, and seamless integration with the apps and tools that developers already know and love. At recent conferences, including NVIDIA GTC Taipei at Computex 2026 and Microsoft Build 2026, these two tech giants unveiled a comprehensive toolkit designed to meet the exploding demand for personal AI agents, featuring everything from secure agent sandboxing to performance improvements that deliver twice the speed for agentic inference. Think of traditional software security like a medieval castle, with high walls and a single heavily guarded gate. Microsoft's new execution containers, or MXC, work more like a modern embassy compound, where different areas have different access levels, and every visitor gets exactly the permissions they need. Nothing more, nothing less. These security primitives allow agents to execute code, work with files, and coordinate tasks across multiple systems, while maintaining strict identity verification and policy enforcement, all built on native Windows operating system foundations that developers can trust. For developers, this solves a critical challenge that's been like walking a tightrope, where agents need access to personal files and applications to be useful. But that same access creates genuine prompt injection risks that could compromise entire systems. NVIDIA's collaboration with Microsoft brings the NVIDIA OpenShell runtime to Windows, built on top of those MXC foundations, like a sophisticated control tower that manages air traffic, providing easy integration packages for developers who want to deploy autonomous, always-on agents safely. OpenShell adds layers of functionality that include policy creation and management, intelligent routing of inference requests, and automatic obfuscation of personally identifiable information, creating a comprehensive framework for secure agent deployment. Popular open-source agents like OpenClaw and Hermes Agent are already looking to leverage these MXC and OpenShell technologies, recognizing them as essential tools for strengthening security when running on Windows systems. At the heart of this personal AI revolution sits NVIDIA's new RTX Spark product family, unveiled at GTC Taipei, featuring small form-factor desktops and laptops that pack the computational punch of a data center into devices that fit comfortably on your desk or in your backpack. These machines deliver 1 petaflop of AI processing power, support up to 128 gigabytes of memory, and include CUDA-accelerated AI frameworks
designed specifically for running large language models alongside your everyday work, like having a supercomputer that doubles as your daily driver. Microsoft is creating a special developer edition called the Surface RTX Spark Dev Box, which comes preloaded with a modified version of Windows that's been configured specifically for developers, along with all the essential development tools you need to start building immediately. NVIDIA Nemotron, their platform for building autonomous AI agents, now supports the full range of NVIDIA client systems, from GeForce RTX gaming cards to professional NVIDIA RTX Pro workstations, and even the powerful DGX Spark and DGX station systems running on Windows. This expansion works through both native Linux and Windows Subsystem for Linux, or WSL, creating a development environment that's like having a Swiss Army knife, where every tool has been perfectly sharpened and calibrated for the specific task of agent development. The latest Nemotron update includes significant enhancements to the installer, making setup more seamless and intuitive, while also adding support for running Hermes Agent as an integrated option within the platform. Hermes Agent itself has released native Windows support this week, complete with both a command line interface for developers who prefer working in terminals and a sleek desktop application that makes the technology accessible to a broader range of users. This dual approach streamlines the user experience while making it much easier for agents to interact directly with native Windows applications, APIs, and file systems, creating the kind of deep integration that makes AI assistants feel natural rather than bolted on. Meanwhile, AI research firm H Company has released their new Hollow 3.1 range of models, which are specifically tuned for something called computer use, a capability that lets agents see your screen and interact with it by clicking and typing, much like a human assistant looking over your shoulder. These models extend agentic capabilities across a much broader range of applications than traditional text-based interactions, and they include quantized checkpoints that use 35% less memory compared to FP8 precision, making them more practical for personal computers with limited resources. H Company has also announced a new computer use harness with support for local models, and with NVIDIA's optimization help, their new models and harness deliver more than twice the performance on NVIDIA GPUs compared to previous versions. Since agents often run continuously, 24 hours a day and 7 days a week, working on increasingly complex tasks, efficient local computation becomes as critical as fuel efficiency in a car that never stops driving. NVIDIA has collaborated extensively with the open source community to enhance the top inference backends that power these agents, focusing particularly on llama.cpp and VLLM, the engines that actually run the language models behind the scenes. The improvements to llama.cpp are particularly impressive, delivering twice the performance on Qwen 3.5 and 3.6 27B dense models, and 1.6 times better performance on the larger Qwen 3.5 and 3.6 35B mixture of expert models. These gains come from two sophisticated techniques, starting with multi-token prediction, or MTP, which works like having a junior assistant who suggests the next few words in a sentence, allowing the main model to verify multiple tokens in a single forward pass, rather than generating them one by one. MTP is particularly practical for developers because it requires no additional training for models that already support the technique, delivering faster throughput while maintaining identical output quality, like getting a speed boost without any trade-offs. The second technique, Programmatic Dependent Launch, or PDL, provides faster decode performance by allowing dependent kernels to execute concurrently on the same CUDA stream, rather than forcing them to wait in line like customers at a single file checkout counter. VLLM, which has already adopted multi-token prediction, is receiving additional optimizations that improve inference performance by 2.6 times, including better BF16 kernel selection for mixture of expert models and reduced runtime overhead through improvements to CUDA graphs. You can start exploring these performance updates immediately through popular tools like LM Studio, llama.cpp, and VLLM, making these improvements accessible to developers at every level of experience. One popular approach to running AI locally has been using multiple GPUs together, like yoking a team of oxen to pull a heavier load, accessing more memory and computational power than any single graphics card could provide. While cloud frameworks like VLLM are already well optimized for multiple GPUs thanks to their widespread use in data centers, PC-focused frameworks like llama.cpp and ComfyUI's PyTorch implementation haven't traditionally been designed with multi-GPU setups in mind. NVIDIA has collaborated with both llama.cpp and ComfyUI to enhance performance specifically for RTX PCs equipped with 2 equivalent GPUs, enabling users to run larger models and harness the computational power of both cards working in harmony. Llama.cpp now supports tensor parallelism, fully utilizing both GPUs to provide up to roughly twice the memory capacity and up to 1.8 times better compute performance, like having 2 expert translators working on different sections of the same document simultaneously. LM Studio has made these multi-GPU changes widely available through their application, and getting started is straightforward. Simply open the LM Studio app, navigate to Settings, then select Runtime to enable tensor parallelism. ComfyUI takes a different approach, integrating the classifier free guidance method to achieve up to twice the computational throughput across 2 GPUs, while also allowing users to split model chains across graphics cards to fully load them into memory. This eliminates the memory swapping overhead that comes with low VRAM mode, providing an additional performance gain that's like the difference between having all your reference books on your desk versus having to fetch them from another room every time you need to look something up. For media and video developers, NVIDIA has made the AI for Media SDK, known as AI for M, available under private access for those building AI-powered video and broadcast pipelines, opening up new possibilities for automated content creation. The lip sync feature has reached general availability, with language-optimized models now supporting French, German, and Spanish, enabling higher quality dubbing and content localization with improved articulation compared to base models. Active Speaker Detection, or ASD, has also reached general availability, bringing enhanced multi-camera and multi-phone support, plus cross-video speaker identification correlation, automating workflows that previously required painstaking manual effort. The broader Windows AI platform continues to mature like a garden reaching full bloom, with Windows ML powered by NVIDIA TensorRT for RTX on NVIDIA GPUs, giving developers multiple pathways to ship GPU-accelerated AI applications. Windows AI Foundry and Windows AI APIs now benefit from GPU acceleration, automatically routing supported API calls to high-performance local inference on NVIDIA GPUs when running on RTX hardware, starting with Phi Silica, a 3.3 billion parameter small language model. Phi Silica specializes in summarization, rewriting, code generation, and other on-device AI tasks, providing a foundation for developers who want to integrate AI capabilities without requiring massive computational resources. The adoption of Windows ML and TensorRT for RTX continues to gain momentum, with 4 notable partners recently upgrading from DirectML and seeing impressive performance improvements across diverse applications. VoiceMod now achieves 42% faster real-time AI voice conversion. Topaz delivers 20% faster 1080p to 4K upscaling, while reducing engine storage requirements by 3 to 4 times. DxO PhotoLab 9.7 ships with faster AI photo processing, and Camo Streamlight's AI Autotune feature intelligently adjusts lighting levels in real time. For developers who need to run Linux applications within Windows, the new Windows Subsystem for Linux Containers, or WSLC, provides a built-in method for creating, running, and interacting with Linux AI containers directly from native Windows applications. This system works like having a universal translator that allows Windows applications to seamlessly communicate with Linux environments, enabling complex, professional-grade development workflows without requiring users to install and manage WSL system resources themselves. Developers can integrate this functionality into their applications using a straightforward C/C++ library, unlocking sophisticated development environments that maintain parity with production workflows, while allowing faster local iteration. This comprehensive ecosystem of tools and optimizations represents a fundamental shift in how AI applications are built, deployed, and used, with the local AI stack on NVIDIA RTX systems now fully ready to support the next generation of intelligent software. With secure agent sandboxing through MXC and OpenShell, dramatically faster inference performance, robust multi-GPU scaling capabilities, and a rapidly maturing Windows AI platform, developers building for the more than 100 million NVIDIA RTX PCs worldwide now have the infrastructure they need to create truly transformative AI applications that feel as natural and reliable as the computers themselves. You've just experienced the current reality of AI agents working alongside people in their daily tasks, and witnessed how NVIDIA and Microsoft are joining forces to make this technology more accessible. Let that collaboration settle in your mind, the way 2 companies are working together to bring something truly helpful into our everyday lives. There's no need to hold on to the technical specifications, just the gentle understanding that smart, caring people are making this technology easier to use. Now we'll explore a fascinating new development, a family of AI models called Holo 3.1 that can work seamlessly across different devices and environments, bringing us closer to truly universal digital assistants. Imagine you're trying to teach a helpful assistant to use your computer the same way you do, whether you're sitting at your desktop, holding your phone, or working on a tablet. And you want that assistant to work just as smoothly, whether it's running on a powerful server in the cloud or quietly humming along on the device right in front of you. This is exactly the challenge that the Holo 3.1 family of models sets out to solve, representing a significant step toward what researchers call universal computer use agents, systems that can operate across different environments, integrate into any software stack, and run wherever your actual work happens to live. Think of Holo 3.1 like a Swiss Army knife that's been redesigned not just to have more tools, but to work equally well whether you're camping in the wilderness, fixing something in your garage, or doing delicate work at a laboratory bench. The core challenge being that a tool that works beautifully in one setting might struggle when the environment changes. Built on the foundation of the Qwen family of models, Holo 3.1 emerged from a pattern that researchers observed repeatedly as teams moved from testing their computer use agents in controlled laboratory conditions to deploying them in the messy, unpredictable world of real production environments. The pattern was always the same. Like a musician who sounds perfect in their practice room, but struggles when they have to perform on a different stage, with different acoustics, different lighting, and a different piano. Strong performance in one carefully controlled setting simply didn't transfer reliably to the countless variations that real-world deployment brings. Mobile devices introduce their own particular flavor of challenges, with touch interfaces, different screen sizes, and interaction patterns that differ fundamentally from the point-and-click world of desktop computing, like trying to paint a detailed landscape with a brush designed for house painting. On Android World, which serves as a comprehensive testing ground for mobile automation capabilities, the improvements are quite substantial, with the flagship 35B A3B model jumping from 67% to 79.3% success rate, while the more compact 4B and 9B variants improved from 58% all the way up to 72%. But mobile environments were just one piece of the puzzle, because in the real world, different teams want to integrate these computer use capabilities into their existing software stacks, each with their own preferred ways of communicating with AI models, like trying to connect a new appliance to a house where every room has different types of electrical outlets. Holo 3.1 addresses this integration challenge by supporting both the structured JSON outputs that were available in the previous Holo 3 version and introducing native support for function calling protocols, giving developers the flexibility to choose the communication style that best fits their existing infrastructure. Across OS World and internal benchmarks covering e-commerce workflows, business software interactions, and collaboration tools, these two different communication approaches now achieve near-parity performance, meaning teams no longer have to sacrifice capability for compatibility. When evaluated inside the company's own HoloTab product harness, Holo 3.1 delivers more than a 25% improvement over its predecessor, like upgrading from a reliable but aging car to a newer model that not only runs more smoothly, but also gets better gas mileage and handles more types of terrain. Recognizing that not every use case requires the computational equivalent of a Formula One race car, the Holo 3.1 family includes smaller model sizes designed for cost-effective and private deployment, with options at 0.8 billion, 4 billion, and 9 billion parameters, alongside the flagship 35 billion parameter model. Think of these different sizes like a fleet of vehicles, each optimized for different jobs, from the ultra-lightweight 0.8B model that's like a nimble motorcycle for quick, simple tasks, up through the balanced 9B model that's like a versatile SUV, all the way to the 35B A3B model that's like a heavy-duty truck capable of handling the most demanding workloads. For the first time in this model family, Holo 3.1 ships with quantized weights, a technique that's like compressing a high-resolution photograph to make it load faster while trying to preserve as much visual quality as possible. Except here, we're compressing the model's numerical precision to make it run faster while preserving its reasoning capabilities. The quantization options include FP8, Q4GGUF, and NVFP4 formats, each representing different points on the trade-off curve between model size, inference speed, and performance retention, like choosing between different compression settings when you're preparing images for different purposes. For the NVFP4 format, the team used NVIDIA's Model Optimizer in a W4A16 configuration, which is a specific way of reducing the precision of the model's weights while keeping the activations at higher precision, like using a lower resolution brush for the broad strokes of a painting while keeping fine detail brushes for the intricate parts. The performance impact of this compression is remarkably small, with both FP8 and NVFP4 achieving the same OS World scores as each other, falling only about 2 points below the full precision BF16 checkpoint, like getting 98% of the original image quality while using significantly less storage space. But the speed improvements are substantial, like upgrading from a scenic mountain road to a well-designed highway, with NVFP4W4A16 delivering 1.41 times the total token throughput of FP8 and 1.74 times that of the full precision BF16 format when running on DGX Spark hardware. The Q4 GGUF checkpoints target an even more ambitious goal, enabling computer use agents to run entirely on consumer hardware, like bringing a capability that once required a dedicated server room into something that can sit quietly on your desk or kitchen table. In this local deployment scenario, the agent itself runs on a regular Windows or Mac machine, while the underlying model can either run on that same consumer device, with reference performance numbers provided for Apple Silicon, or on a more powerful DGX Spark system connected to the same local network. Either way, the entire system operates like a self-contained ecosystem, with all executions staying fully private and local, nothing leaving the user's network, like having a skilled assistant who works entirely within your home office rather than needing to make phone calls to a distant headquarters for every decision. The engineering optimizations developed in collaboration with NVIDIA, combined with the NVFP4 quantization, deliver a compound speedup of approximately 2 times end-to-end compared to the FP8 baseline, cutting the average time per agent step from 6.8 seconds down to 3.3 seconds. This improvement in response time transforms the user experience from something that feels like waiting for a thoughtful but slow colleague to respond, to something more like having a conversation with someone who thinks quickly and responds promptly, making the interaction feel much more natural and fluid. The complete Holo 3.1 family spans 4 different model sizes, each targeting different deployment scenarios, from the ultra-lightweight 0.8B model for the most resource-constrained environments, through the cost-efficient 4B and balanced 9B options, up to the 35B A3B model for applications that demand state-of-the-art performance above all other considerations. Like a toolbox that's been carefully curated to handle everything from delicate electronics repair to heavy construction work, these optimized checkpoints in FP8, NVFP4, and Q4 GGUF formats give developers the flexibility to choose exactly the right balance of performance, speed, and resource requirements for their specific use case. The models are available through multiple channels, including the Holo Models API for cloud-based deployment, and Hugging Face for researchers and developers who want to download and experiment with the models directly, making it easy for teams to get started regardless of their preferred development workflow. As you drift towards sleep, you might imagine this family of models as a quiet revolution in how we think about AI assistants, moving from systems that live in distant data centers and work only in carefully controlled conditions, towards something more like a trusted companion that can adapt to whatever environment you find yourself working in, running locally and privately while maintaining the intelligence and capability you need to get real work done. I'm curious how this one sits with you. Does the idea of where all of this is heading comfort you or quietly unsettle you? Tell me in the comments. I read them on my own sleepless nights. We've just discovered Holo 3.1, those remarkable models designed to work as smoothly on your phone as on your desktop, like digital assistants that can follow you wherever your work takes you. Let yourself rest with that comforting thought, knowing that the future holds helpers that can adapt to any environment you find yourself in. You needn't worry about remembering every detail about how they work. Just feel the reassurance that such flexible assistance is being carefully developed. Now, let's gently shift our focus to understand why these persistent, long-running agents need such different care and feeding than the software we're used to, and how our devices are learning to welcome these new kinds of digital residents. Imagine your laptop as a cozy cottage that was designed for weekend guests, where visitors drop by for a few hours, use some resources, then politely leave so the next person can settle in. Traditional software applications behave much like these considerate guests, running for specific tasks, completing their work, then gracefully exiting to free up memory and processing power. But autonomous agents, the kind that can reason, plan, and execute complex workflows over hours or days, are more like permanent residents who've decided to move in with all their belongings, set up multiple ongoing projects, and invite their friends to stay indefinitely. The fundamental shift here isn't just about computational intensity. It's about persistence and concurrency in ways that most consumer hardware simply wasn't architected to handle. When we talk about long-running agents, we're describing software entities that maintain continuous operation, often spawning multiple concurrent processes, while accumulating vast amounts of contextual information that must remain readily accessible in memory. Patterns that emerged prominently with large language models, capable of maintaining extensive conversational context. Think of context windows like an artist's workspace, where traditional applications might use a small desk with just enough room for a single sketchpad and a few pencils. These agents, however, need something more like an airplane hangar, with multiple easels, reference materials covering the walls, work-in-progress canvases scattered throughout, and enough space for several artists to collaborate simultaneously. The context windows we're seeing in modern language models can stretch to hundreds of thousands, even millions of tokens, and agents often need to maintain this entire workspace in active memory. Your typical laptop or desktop machine allocates memory with the assumption that applications will come and go, much like a restaurant that sets tables, serves customers, then clears and resets for the next party. The memory management systems expect this natural ebb and flow, this breathing room between intensive tasks. But autonomous agents break this assumption entirely, requiring sustained access to enormous chunks of RAM, while simultaneously demanding consistent processing power for ongoing inference, planning, and decision-making operations. The hardware stress becomes particularly acute when you consider that these agents don't just think in isolation. They spawn additional processes like a master chef who needs multiple sous chefs working different stations simultaneously. One process might be handling natural language processing, another managing tool interactions, a third maintaining conversation history, and yet another coordinating with external APIs or databases. Each of these processes demands its own slice of memory and computational resources. Local GPUs, even high-end consumer cards, face a challenge similar to trying to host a multi-day music festival in your backyard. The hardware might handle a single intense performance beautifully, running inference on a large language model for a few minutes or even an hour. But when that same level of intensity needs to be sustained for days, with multiple concurrent models potentially running, thermal management becomes critical. Power consumption skyrockets, and the sustained load can push components beyond their intended operating parameters. Memory bandwidth presents another bottleneck that's often overlooked in traditional computing scenarios. Picture the difference between a narrow hiking trail that works perfectly fine for occasional walkers versus trying to accommodate a constant stream of heavy equipment and supply trucks. Agents continuously shuttle vast amounts of data between system RAM, GPU memory, and storage, creating sustained bandwidth demands that can saturate even high-end consumer memory subsystems, challenges that become particularly acute with the attention mechanisms in modern transformer architectures. The storage implications are equally dramatic, as these agents often maintain persistent memory systems that grow continuously over time. Unlike traditional applications that might write occasional log files, autonomous agents frequently implement sophisticated memory architectures, maintaining detailed interaction histories, learned patterns, and contextual associations. This isn't just about storage capacity. It's about the sustained read-write operations that can wear down consumer SSDs
much faster than typical usage patterns, particularly when models need efficient access to large key-value caches. Consider the thermal envelope of your machine, like the climate control system in a greenhouse designed for temperate plants, where autonomous agents are essentially tropical orchids that need sustained warmth and humidity. Consumer cooling solutions, whether air or liquid, are typically designed around burst workloads, the kind where components heat up during intensive tasks, then cool down during idle periods. Agents eliminate these cooling opportunities, creating sustained thermal loads that can push even well-designed cooling systems to their limits. The power supply faces similar challenges, transforming from something like a variable speed water pump that adjusts flow based on garden needs to a system that must maintain maximum pressure continuously. Many consumer power supplies are rated for peak loads, but not necessarily designed for sustained operation at those levels. The efficiency curves, heat generation, and component longevity all change dramatically under constant high-load conditions. Network connectivity adds another layer of complexity, as these agents often maintain persistent connections to multiple external services, APIs, and data sources. Your home internet connection, which handles bursty web browsing and occasional large downloads beautifully, suddenly becomes like a small-town post office trying to handle the mail volume of a major metropolitan area. The sustained bandwidth requirements, connection pooling, and reliability demands can overwhelm consumer-grade network infrastructure. The concurrency model of autonomous agents creates resource contention patterns that most consumer operating systems struggle to manage efficiently. Imagine a library designed for quiet individual study, where suddenly multiple research teams arrive, each needing access to different sections simultaneously, constantly moving between resources, and requiring the librarian's attention for complex requests. The operating system's scheduler, memory allocator, and I/O systems face coordination challenges they were never optimized for, particularly when serving multiple concurrent language model instances with dynamic memory requirements. When multiple agents run simultaneously, which is increasingly common in complex workflows, the resource multiplication becomes exponential rather than linear. It's like the difference between cooking a single elaborate meal versus running a restaurant kitchen during peak hours, where every dish requires different ingredients, cooking times, and attention. But they all need to be prepared simultaneously without compromising quality. The debugging and monitoring challenges compound these hardware stresses, as traditional system monitoring tools often can't provide the granular visibility needed to understand where bottlenecks are occurring in complex agent workflows. You're essentially trying to diagnose performance issues in a busy factory using tools designed for monitoring a single workbench, missing the intricate interdependencies and resource flows that determine overall system performance. Storage I/O patterns shift dramatically from the predictable read-heavy or write-heavy patterns that consumer SSDs are optimized for, toward complex mixed workloads with frequent random access patterns. Think of it like a filing system designed for sequential document storage suddenly being used for a complex cross-referencing research project, where every piece of information connects to multiple others, creating access patterns that stress the storage subsystem in unexpected ways. The economic implications become significant when you realize that consumer hardware pushed into these sustained high-load scenarios often experiences accelerated wear and reduced lifespan. Components that might last 5 to 7 years under typical usage patterns may need replacement in 2 to 3 years, transforming the total cost of ownership calculation entirely. It's like using a family sedan for daily taxi service, where the increased utilization fundamentally changes maintenance schedules and replacement timelines. Enterprise hardware, designed with these sustained workload patterns in mind, incorporates features like error-correcting memory, redundant cooling systems, and components rated for continuous operation that simply aren't present in consumer systems. The difference
is like comparing a residential HVAC system to industrial climate control, where the fundamental engineering assumptions about duty cycles, reliability requirements, and failure modes are completely different, particularly important for systems running continuous reinforcement learning from human feedback workflows. As autonomous agents become more sophisticated and widely deployed, we're witnessing the emergence of entirely new hardware requirements that bridge the gap between consumer and enterprise computing. The future likely holds specialized hardware designed specifically for agent workloads, optimized for sustained high-context inference, efficient memory management, and the unique resource patterns these persistent intelligent systems demand. You've just learned about how AI agents are like permanent residents rather than temporary guests, requiring our computers to adapt to their constant presence and ongoing needs. Take a moment to let this shift in perspective settle, the way our machines are evolving to host these thinking, persistent companions. There's something almost touching about imagining our devices learning to care for these digital minds that want to stay and help. Now we'll explore how these agents have grown from simple chatbots into something far more sophisticated, companions that can reason alongside you for days or weeks, thinking through complex problems and maintaining rich, ongoing conversations about your work. Picture a chatbot that was once like a helpful librarian behind a desk, answering single questions before you walked away, now evolving into something more like a dedicated research assistant who stays with you for hours, days, or even weeks, thinking through complex problems, using tools, calling in specialists, and maintaining a running conversation about your project as it unfolds. These long-running AI agents represent a fundamental shift in how we think about artificial intelligence systems, moving from simple question and answer interactions to persistent, reasoning companions that can orchestrate complex workflows, maintain context across extended sessions, and coordinate with other agents to tackle multifaceted challenges. But here's where things get tricky. Like a conversation that keeps growing longer and longer, with each participant adding more detail, more context, more reasoning steps, until the simple exchange has become a thick folder of documents that everyone needs to reference before speaking. As these agents work, they constantly communicate, planning their next moves, calling tools, invoking subagents, receiving information, and then passing all that history, all those outputs, all those reasoning steps back into the model continuously, causing token counts to balloon and costs to spiral upward, while the risk of losing sight of the original goal increases with each exchange. The solution, NVIDIA suggests, is like having a well-organized kitchen with different chefs for different tasks, where you have frontier reasoning models acting as the head chef for orchestration and complex planning, while efficient models handle the high-volume execution, validation, and tool calling that make up the bulk of the work. Enter NVIDIA Nemotron 3 Ultra, an open model designed specifically to help long-running agents complete their tasks faster while keeping costs manageable. Like having that perfect head chef who can think deeply when needed, but doesn't waste time or resources on routine decisions. Nemotron 3 Ultra is a 550 billion parameter mixture of experts model with 55 billion active parameters, built specifically for frontier reasoning and orchestration in agentic systems, where the architecture is like having a vast library of specialists, but only calling upon the relevant experts for each particular challenge. Think of most agent workflow calls as routine maintenance, like checking gauges and flipping standard switches. But then there's that critical subset that demands deeper reasoning, the moments when you need to sustain architectural decisions across lengthy coding sessions, synthesize contradictory evidence from hundreds of research sources, or verify chip designs against thousands of constraints. The performance numbers tell an interesting story, with Nemotron 3 Ultra achieving 91% on agent productivity pinch bench, though trailing slightly behind competitors like GLM 5.1 in long horizon planning at 33% versus 40%, while excelling in instruction following at 82% and maintaining impressive long context performance at 95% accuracy with 1 million token contexts. Speed matters tremendously in this context, and Nemotron 3 Ultra achieves 5 times higher throughput compared to other open models in its class, like having a sports car engine where others have reliable but slower sedans, enabling those long-running agents to complete their tasks faster and more efficiently. Efficiency runs deeper than just speed, though, like a well-tuned machine that not only runs faster but uses less fuel, with experiments on SWI Bench and Terminal Bench 2.0 showing that Nemotron 3 Ultra completed benchmarks using fewer total tokens and fewer tokens per turn than comparable models, lowering costs for agentic tasks by up to 30%. The architectural innovations behind Nemotron 3 Ultra tackle the typical efficiency-accuracy trade-offs that plague high-capacity reasoning models, like an engineer finding clever ways to make a powerful system run more smoothly without sacrificing its strength. The post-training approach focuses specifically on agent harnesses rather than just single-turn chat, like training a musician not just to play individual notes beautifully, but to perform in complex ensemble pieces where they must listen, respond, coordinate, and maintain their part across long, intricate compositions. This training uses NVIDIA's Nemorl and GIM open libraries with one of the largest suites of long-running, task-solving, tool-using datasets in the world, preparing the model for workflows where agents plan, call tools, read observations, delegate to subagents, validate outputs, and recover from errors across many turns. The hybrid Mamba transformer architecture is like having two different types of memory systems working together, where Mamba layers act like a flowing stream that efficiently processes long sequences, while transformer layers function like a precise filing cabinet that preserves exact recall when agents need to retrieve specific facts from large context windows. NVFP4 precision represents a practical breakthrough, like having a universal key that works across different locks, where the same checkpoint runs seamlessly on NVIDIA Hopper, Blackwell, and Ampere GPUs, giving developers the flexibility to use one model across all NVIDIA GPU architectures while delivering up to 5 times higher throughput per GPU compared to BF16 on Blackwell. Latent MoE supports more efficient expert routing, like a sophisticated telephone switchboard operator who instantly connects callers to exactly the right specialist, enabling the model to handle diverse workflows spanning reasoning, code generation, tool calls, and domain-specific logic without wasting computational resources on irrelevant experts. Multi-token prediction works like a chess player who thinks several moves ahead in a single moment of contemplation, helping reduce generation time by predicting multiple future tokens in a single forward pass, which significantly improves throughput for long outputs and multi-turn workflows. The multi-teacher on-policy distillation approach, or MOPD, represents something like a graduate student learning from more than 10 specialized professors simultaneously, where each teacher has their own domain-specific expertise and scores the student's work in their particular area, helping the model improve reasoning across domains more efficiently than traditional single-teacher methods. During MOPD training, the student model generates attempts across various domains, while receiving dense feedback signals from the corresponding teacher models, like a workshop where the student creates projects while multiple master craftspeople provide real-time guidance, with the entire process running asynchronously, so that student work generation, teacher evaluation, and student improvement happen in a fully pipelined flow. The process becomes iterative and self-improving, like a garden where each season's harvest provides seeds for an even better garden the next year, with new rounds of teacher training initialized from the updated student model, creating a co-evolution between students and teachers that enables continuous capability improvement and progressively stronger specialization. The training data foundation builds upon a 10 trillion token base with an additional 212 billion targeted tokens addressing specific domain gaps, like renovating a house by adding carefully chosen rooms where they're most needed. These additions include 4 billion tokens of synthetic legal data that increased proxy legal bench performance from 64.6% to 74.7%. 35 billion tokens of synthesized wiki-based data, boosting simple QA scores from 40.2% to 50.2%, and 173 billion refreshed GitHub tokens, updated through September 30th, 2025. The release also includes 10 million new supervised fine-tuning samples, 1 million new reinforcement learning tasks across multiple domains, and 15 entirely new RL environments, bringing the cumulative Nemotron open data totals to 50 million SFT samples, 2 million RL tasks, and 55 RL environments, like adding new tools and materials to an already well-stocked workshop. These improvements translate to real-world performance with SWEbench verified scores ranging between 65% and 70.4% across different frameworks including Pi, OpenHands, Hermes, OpenCode, and Mini Sweb Agent, demonstrating consistent performance regardless of which deployment framework developers choose. For customization, Nemotron 3 Ultra supports fine-tuning through LoRa, supervised fine-tuning, and reinforcement learning using NVIDIA's Nemo libraries, like having a modular toolkit where developers can adjust and adapt the model to their specific domain needs using well-documented recipes and established procedures. The deployment options span a comprehensive ecosystem, from Dynamo recipes that support KV-aware routing and multi-token prediction to integration with leading agent frameworks, making the model accessible through platforms like Perplexity, OpenRouter, Anaconda, and build.nvidia.com, like having multiple doorways into the same powerful building. For safety-conscious deployments, the system integrates with NVIDIA NemoClaw and OpenShell, where NemoClaw acts like a blueprint that ties the environment together with a single command, installing the OpenShell runtime to provide a secure environment for running autonomous agents more safely alongside open-source models. 2 companion models round out the release, with Nemotron 3.5 Content Safety serving as a 4 billion parameter guardrail model that works like a vigilant security guard, classifying unsafe or policy-violating content across text, images, and combined inputs in 23 safety categories and 12 languages. Nemotron 3.5 ASR brings voice capabilities with sub-100 millisecond latency for real-time voice orchestration, using the same cache-aware streaming architecture as its English predecessor, but now supporting over 40 languages in a single checkpoint, like having a polyglot interpreter who can switch between languages instantly without missing a beat. The licensing has evolved to OpenMDW 1.1, the Linux Foundation's permissive license designed specifically for OpenAI model distributions, covering the full set of model materials, including architecture, parameters, documentation, and software under a single framework, like having a comprehensive deed that clearly defines what you can do with every part of the property. This represents more than just a model release. It's a complete ecosystem for building, deploying, and running sophisticated AI agents that can reason over long horizons, maintain context across extended interactions, and coordinate complex workflows while managing costs and maintaining safety, like having not just a powerful engine, but the entire vehicle, the roads to drive on, and the map to navigate toward your destination. We've just witnessed the beautiful evolution from simple question and answer chatbots to persistent reasoning companions that can work alongside you for extended periods. Rest with the wonder of that transformation, how artificial minds have learned to maintain context and conversation across time, becoming true thinking partners. You don't need to grasp every technical detail about how they manage their growing memory. Just appreciate the remarkable journey from basic responses to genuine collaboration. Now let's explore some of the technical challenges researchers have faced in making these systems work efficiently, starting with groundbreaking work from 2022 that helped make large-scale AI inference possible. Back in 2022, researchers at Google published work on efficiently scaling transformer inference, tackling one of the most challenging problems in deploying large language models. Serving 500 billion parameter models with tight latency requirements and long sequence lengths. Like a master chef organizing a vast kitchen where every ingredient must be precisely positioned and every cooking station must coordinate seamlessly, the researchers developed systematic approaches to partition massive models across hundreds of accelerator chips, while minimizing the communication overhead that typically bottlenecks such distributed systems. The core challenge they addressed was that generative inference proceeds one token at a time, with each new token depending on all previously generated tokens, making it fundamentally different from the highly parallel training process. Like a factory assembly line, where each station must wait for the previous one to finish before starting its work. This sequential dependency creates bottlenecks that become more severe as models grow larger and require distribution across more chips, with the researchers focusing specifically on TPU v4 systems with their three-dimensional torus topology. Their analytical framework revealed that inference costs break down into memory costs and compute costs, with memory costs dominated by loading model weights and the key value cache from high bandwidth memory to compute cores. Like a librarian who must retrieve specific books from vast archives for each reader's request, the system must transfer these large tensors from memory once per forward pass, with the key value cache growing particularly large at longer sequence lengths, reaching 3 terabytes for a 500 billion parameter model with batch size 512 and context length 2048. Or the feed-forward layers. They developed 3 partitioning strategies optimized for different scenarios, starting with 1D weight stationary partitioning, where weight matrices are sharded along one dimension, requiring communication that remains constant regardless of chip count. Like a relay race where the baton must be passed completely between each runner. This approach transfers entire activation matrices between chips via all gather and reduce scatter operations, with communication time of 2 BLE divided by network bandwidth, where B is batch size, L is sequence length, and E is model dimension. The 2D weight stationary approach partitioned weight matrices along both input and output dimensions, creating roughly square shards that enabled more efficient communication scaling. Like a chessboard, where pieces can move both horizontally and vertically to reach their destinations more efficiently. This strategy alternated aggregation between the model dimension and feed-forward dimension, achieving communication time that scales as the inverse square root of chip count rather than remaining constant, specifically 8 BLE divided by the square root of chips times network bandwidth. For large batch sizes, they introduced weight-gathered layouts that kept activation stationary while transferring weights between chips, recognizing that when batch sizes grow large enough, the activation tensors become significantly larger than the weight tensors. Like a postal system that switches from having customers collect mail at a central office to having postal workers deliver mail to each house when the customer base becomes large enough. This approach minimized total data movement by choosing the smaller payload to transfer, with optimal communication time scaling as the square root of batch size times sequence length. Their attention layer optimizations focused particularly on multi-query attention, where multiple query heads share a single key value head, reducing memory requirements, but requiring different partitioning strategies than traditional multi-head attention. Like a lecture hall, where one professor speaks to multiple groups of students, rather than having separate professors for each group. Multi-query attention reduces the key value cache size by a factor equal to the number of heads, but only if partitioned correctly across the batch dimension rather than the head dimension to preserve these memory savings. The key insight for multi-query attention was partitioning the query, key, and value matrices across the batch dimension rather than the head dimension, reducing per-chip memory costs by a factor equal to the number of chips. Like a restaurant where instead of each waiter carrying full trays to their assigned sections, the kitchen divides each dish among all waiters, who then serve their portion to customers throughout the restaurant. This approach required additional all-to-all communication for the small query tensors, but dramatically reduced memory loading time for the much larger key value cache. They distinguished between two phases of inference with fundamentally different performance characteristics. Prefill, where input tokens can be processed in parallel, and decode, where output tokens must be generated sequentially. Like a theater where the audience enters simultaneously during seating, but exits one row at a time during the performance, prefill benefits from high parallelism and weight-gathered strategies at large batch sizes, while decode operates on single tokens and favors weight-stationary approaches that minimize per-step communication overhead. The parallel attention and feed-forward formulation used in Palm provided additional optimizations by computing both layers simultaneously from the same input and summing their outputs, like two chefs working on different parts of the same meal in parallel, rather than one waiting for the other to finish. This approach eliminated half the communication operations per transformer layer and enabled matrix multiplication fusion for better hardware utilization, while also reducing the number of layer normalization operations from 2 to 1 per layer. Low-level optimizations included the looped collective einsum technique that overlapped communication with computation, hiding much of the data transfer latency behind useful work. Like a skilled juggler who catches one ball while simultaneously throwing another, the system performed matrix multiplications on one data partition while transferring the next partition in the background, achieving approximately 1.4 times better performance than simpler compiler-scheduled implementations and enabling some memory-intensive configurations that would otherwise be impossible. For quantization, they used 8-bit integer weights instead of 16-bit floating point, without significant quality degradation, effectively halving the memory footprint of model parameters. Like a photographer who compresses images to smaller file sizes while maintaining visual quality, this quantization reduced memory bandwidth requirements and enabled fitting larger models or batch sizes within the same hardware constraints, contributing to their achieved latency targets. Their performance evaluation on Palm models demonstrated concrete results. For the 540 billion parameter model, running on 64 TPU v4 chips, they achieved 29 milliseconds per token during generation with int8 quantization, and 76% model flops utilization during large batch input processing. Like a high-performance race car that achieves both quick acceleration and efficient fuel consumption depending on track conditions, their system delivered both low-latency interactive performance and high-throughput batch processing while supporting 2048 token context lengths. The practical impact translated to real application scenarios. An interactive chatbot using Palm 540B could process 64 input tokens, consult 1920 tokens of conversation history, and generate a 64-token response in just 1.9 seconds total. Like a skilled translator who quickly reads a document, recalls previous context, and provides a fluent response, the optimized system met the stringent latency requirements for interactive applications, while maintaining the model's full capabilities and long context understanding. For throughput-oriented offline applications, Their implementation processed 1984 input tokens and generated 64 output tokens with 73% overall flops efficiency across large numbers of examples. Like a printing press that efficiently processes thousands of pages once properly set up and running, the system maximized hardware utilization for batch workloads where latency was less critical than cost-effective token processing, demonstrating the versatility of their partitioning framework. The analytical framework they developed enabled users to systematically choose optimal configurations based on their specific requirements, rather than relying on exhaustive search across partitioning strategies. Like an architect who provides engineering principles and mathematical formulas rather than just blueprints for specific buildings, their approach offered intuitive understanding of the trade-offs between model size, sequence length, chip count, and application requirements, making it broadly applicable beyond their specific experimental setup. Their work established new performance frontiers that outperformed existing benchmarks like faster transformer, particularly in the challenging regime of very large models with long contexts and tight latency constraints. Like mountaineers who established new routes to previously inaccessible peaks, the researchers demonstrated that careful engineering and systematic optimization could push the boundaries of what was considered feasible for large language model inference, opening possibilities for more demanding real-world applications. The scaling behavior they characterized showed how optimal strategies shift as system parameters change. 1D partitioning works well for smaller chip counts. 2D partitioning becomes beneficial beyond 16 chips, and weight-gathered approaches excel at large batch sizes. Like a navigation system that recommends different routes depending on traffic conditions, time of day, and destination, their framework provided guidance for selecting the most efficient approach based on the specific constraints and requirements of each deployment scenario. Memory optimization emerged as a critical factor, with the key value cache often dominating inference costs, especially for multi-head attention at long sequence lengths, where it could grow 3 times larger than the model parameters themselves. Like a warehouse manager who must carefully organize inventory to minimize retrieval time, the researchers showed that intelligent memory layout and partitioning strategies could dramatically reduce the time spent loading cached data from memory, enabling much larger context lengths and batch sizes than previously practical. Looking back from today's perspective, this 2022 work laid important groundwork for the efficient deployment of large language models that became crucial as these systems moved from research prototypes to production services. Like bridge engineers whose careful analysis of load-bearing structures enables safe passage for countless travelers, the researchers' systematic approach to understanding and optimizing inference bottlenecks provided the engineering foundation that made large-scale language model deployment economically viable and responsive enough for interactive applications. Someone else is awake right now, listening to this very moment with you. If that's you, leave a word below, so the rest of us know we're not alone at this hour. You've just encountered the intricate world of scaling transformer models, where researchers work like master chefs, coordinating vast, complex systems to serve AI efficiently. Let that image of careful orchestration rest gently in your mind, knowing that brilliant people are solving these challenges so that powerful AI can reach your personal device. There's no need to retain the technical complexities, just the quiet confidence that these problems are being thoughtfully addressed. Now we'll journey back to meet Palm, a groundbreaking language model from 2022 that demonstrated what becomes possible when we scale AI systems to unprecedented sizes, paving the way for the personal agents we're exploring tonight. Back in 2022, a team at Google Research set out to push the boundaries of language model scaling, much like explorers charting new territories with increasingly powerful vessels. They trained Palm, the Pathways language model, a 540 billion parameter autoregressive transformer,
that represented one of the largest dense language models created at that time. The model was trained on 780 billion tokens of high-quality text using Google's new Pathways system, which enabled efficient training across 6,144 TPU v4 chips spanning 2 data center pods. This work continued the scaling trend established by GPT-3, demonstrating that larger models could still yield significant improvements in few-shot learning capabilities across hundreds of natural language understanding and generation tasks. The architecture of Palm followed a standard decoder-only transformer design, but with several key modifications that acted like precision instruments in a master craftsman's workshop. The researchers used SWI-glue activations instead of standard ReLU, which required 3 matrix multiplications rather than 2, but provided better quality. They implemented parallel layers where the MLP and attention computations could run simultaneously rather than sequentially, yielding roughly 15% faster training. Multi-query attention shared key and value projections across heads while maintaining separate query projections, and rope embeddings handled positional information more effectively than absolute position embeddings. The vocabulary used sentence piece with 256,000 tokens, completely lossless and reversible, splitting numbers into individual digits and preserving all white space. The training dataset resembled a carefully curated library spanning diverse domains of human knowledge and creativity. It contained 780 billion tokens, drawn from filtered web pages, 27%, social media conversations in multiple languages, 50%, English books, 13%, Wikipedia articles in various languages, 4%, GitHub source code repositories, 5%, and English news articles, 1%. The source code component included 24 programming languages from open source repositories, with copyleft licenses excluded and duplicates removed using Levenshtein distance. The multilingual corpus covered over 100 languages, though approximately 78% remained English content, with the dataset mixture carefully balanced to avoid repeating data across any component during the single training epoch. The training infrastructure operated like a sophisticated orchestra, conducting thousands of musicians in perfect synchronization across 2 concert halls. Palm 540B utilized 6,144 TPU v4 chips across 2 pods connected by data center network, achieving remarkable efficiency without pipeline parallelism. Each pod contained a full copy of model parameters partitioned using 12-way model parallelism and 256-way fully sharded data parallelism. The Pathways system enabled 2-way data parallelism at the pod level, where a single Python client dispatched training batches to each pod, which then computed gradients and exchanged them across the 81 terabits per second burst traffic between pods. This approach achieved 97% of perfect weak scaling efficiency, nearly doubling throughput compared to single pod training. Training efficiency measurements revealed Palm's performance like a high-precision gauge measuring the output of a finely tuned engine. The researchers introduced model flops utilization, MFU, as a more meaningful metric than the traditional hardware flops utilization, since MFU accounts only for required forward and backward pass operations, rather than implementation-dependent rematerialization. Palm 540B achieved 46.2% MFU and 57.8% hardware flops utilization, significantly outperforming previous large models, GPT-3's 21.3% MFU, Gopher's 32.5%, and Megatron Turing NLG's 30.2%. The high efficiency resulted from optimized parallelism strategies, XLA TPU compiler optimizations, and the parallel layer architecture, representing a substantial advancement in large language model training efficiency. The training process followed established procedures with several refinings, functioning like a master chef's recipe refined through years of experience. Weight initialization used fan-in variance scaling, with the add-a-factor optimizer
providing parameter scaling benefits over standard Atom.
Learning rates started at 10 to the negative 2 for 10,000 steps, then decayed proportionally to 1 over the square root of k, where k represented the step number. Sequence length remained fixed at 2048 tokens, with concatenated examples split at exact boundaries. Batch sizes increased progressively during training. 512, 1 million tokens until step 50,000, then 1,024, 2 million tokens until step 115,000, and finally 2,048, 4 million tokens through completion at step 255,000. The framework maintained bitwise deterministic reproducibility, enabling exact replication from any checkpoint. Training stability presented challenges like unexpected storms, disrupting an otherwise smooth voyage across uncharted waters. The largest model experienced approximately 20 loss spikes at irregular intervals despite gradient clipping, a phenomenon not observed in smaller models. These spikes appear to result from specific combinations of data batches and particular model parameter states, rather than inherently problematic data, as the same batches processed from different checkpoints did not reproduce spikes. The researchers developed a pragmatic mitigation strategy, restarting from checkpoints roughly 100 steps before spikes and skipping 200 to 500 problematic data batches. This approach successfully prevented spike recurrence at the same training points, though more principled solutions remained for future investigation. Evaluation on English natural language processing tasks demonstrated Palm's capabilities like a master student excelling across diverse academic subjects. The researchers tested 3 model sizes, 8B, 62B, and 540B parameters on 29 established benchmarks, including open domain question answering, trivia QA, natural questions, web questions, close and completion tasks, Lambda, HelloSwag, story close, Winograd style tasks, common sense reasoning, PIQA, ARC, open book QA, reading comprehension, drop, co-QA, QAC SQAD2 race, superglue tasks, and natural language inference. Palm 540B achieved new few-shot state-of-the-art results on 28 out of 29 benchmarks, typically by significant margins compared to previous models including GPT-3, Gopher, Chinchilla, Megatron Turing NLG, GLAM, and Lambda. The Big Bench evaluation revealed fascinating scaling behaviors resembling sudden phase transitions in physical systems under increasing pressure. This benchmark suite contained over 150 challenging language understanding and generation tasks, many difficult even for humans. Palm 540B achieved breakthrough performance, often surpassing average human performance on the aggregate benchmark. Remarkably, roughly 25% of tasks showed discontinuous improvements when scaling from 62B to 540B parameters, where performance jumped dramatically rather than following smooth scaling laws observed between 8B and 62B parameters. These discontinuous improvements suggested that new capabilities emerged only when models reached sufficient scale, indicating that the benefits of scaling had not plateaued at previously studied model sizes. Multi-step reasoning tasks showcased Palm's problem-solving abilities like a detective, methodically working through complex cases with logical chains of evidence. When combined with chain-of-thought prompting techniques, Palm 540B achieved breakthrough performance on mathematical and common-sense reasoning benchmarks that traditionally required task-specific fine-tuning, domain-specific architectures, or specialized verifiers. The model demonstrated exploratory capabilities in generating explicit explanations for complex reasoning chains, often matching or outperforming fine-tuned state-of-the-art approaches through simple few-shot evaluation. These results indicated that sufficiently large language models could acquire sophisticated reasoning abilities without specialized training procedures, representing a significant advancement in general-purpose language understanding and generation.
Code generation capabilities emerged like a skilled programmer's toolkit, expanding to encompass multiple programming languages and paradigms. Despite source code representing only 5% of training data, Palm demonstrated strong performance on programming tasks across the 24 languages included in the training corpus: Java, HTML, JavaScript, Python, PHP, C#, XML, C++, C, and others. The model showed particular strength in generating syntactically correct code, understanding programming concepts, and translating between different programming languages. The 196 gigabytes of filtered, deduplicated source code from open-source repositories provided sufficient signal for the model to acquire substantial programming knowledge, suggesting that large language models could serve as effective coding assistants even with relatively modest code training data proportions. Multilingual evaluation revealed Palm's linguistic versatility, functioning like a polyglot scholar navigating diverse cultural and linguistic landscapes. Despite approximately 22% non-English content in training data, the 540 billion model achieved remarkable performance on machine translation, summarization, and question answering across numerous languages. Few-shot evaluation results bridged the gap with prior fine-tuned state-of-the-art approaches on non-English summarization tasks and outperformed previous state-of-the-art on translation benchmarks. The model's multilingual capabilities extended beyond major world languages to include many lower resource languages represented in the training corpus, though the researchers noted that future work should investigate the impact of increasing multilingual data proportions on both English and non-English task performance. Bias and toxicity analysis uncovered concerning patterns like shadows lurking beneath the surface of an otherwise impressive achievement. The researchers conducted comprehensive evaluations across multiple dimensions, finding mixed results regarding model behavior. On gender and occupation bias, accuracy on the Winnow gender coreference task improved with model scale, with Palm 540B achieving new state-of-the-art results in few-shot settings. However, co-occurrence analysis on race, religion, and gender prompt continuations revealed the model's tendency to affirm harmful stereotypes, such as associating Muslims with terrorism and violence. Toxicity analysis showed slightly higher overall toxicity levels for larger models, though model-generated continuations correlated more strongly with prompt toxicity than human-generated text, suggesting greater sensitivity to input style rather than inherent toxicity generation. Memory and contamination analysis examined whether Palm simply recalled training data like a student relying on memorized answers rather than true understanding. The researchers investigated training data memorization patterns across model scales and found that larger models showed increased memorization of training sequences, particularly for more frequent or distinctive text patterns. Dataset contamination analysis checked for overlap between training data and evaluation benchmarks, finding some degree of contamination across various tasks, but noting that performance improvements often exceeded what contamination alone could explain. The memorization behavior appeared to scale predictably with model size, suggesting that while larger models did memorize more training content, they also developed genuine language understanding capabilities beyond simple recall. Looking back from our current vantage point in 2026, Palm represented a pivotal moment in language model development, serving as a bridge between earlier scaling efforts and today's more sophisticated approaches. The work demonstrated that scaling laws continued beyond previously explored regimes, with discontinuous improvements suggesting emergent capabilities at larger scales. The efficient training methodology using pathways and the introduction of model flops utilization as a standardized efficiency metric influenced subsequent large model training approaches. While Palm's bias and toxicity issues foreshadowed ongoing challenges in responsible AI development. Its strong performance across diverse tasks and languages provided a foundation for the more capable and better aligned language models that followed in the years since its publication. You've just met Palm, that remarkable 540 billion parameter model that showed us what becomes possible when language models grow to truly massive scales. Let yourself rest in appreciation of that achievement, the way researchers pushed boundaries to show us new possibilities for AI understanding and capability. You needn't hold on to the technical architecture details, just the sense of wonder at how far these systems have come. Now, we'll explore another crucial breakthrough. This one focused on making these powerful models run more efficiently, solving memory management problems that were quietly limiting how well AI systems could serve their users. Back in 2023, researchers at UC Berkeley identified a critical bottleneck in serving large language models that was quietly strangling performance across the industry. Much like a busy restaurant kitchen, where the walk-in cooler keeps running out of space for ingredients, forcing chefs to work with smaller batches and slower service. The team, led by Woo-Suk Kwon and colleagues, observed that while LLMs were becoming increasingly powerful, the systems serving them were wasting enormous amounts of precious GPU memory through inefficient management of what's called the key-value cache, or KV cache, the temporary storage that holds context from previous tokens to generate new ones in sequence. The core problem resembled a parking garage, where every visitor had to reserve an entire floor, regardless of whether they were staying for 20 minutes or 8 hours, leaving vast stretches of prime real estate completely unused while other customers circled endlessly looking for space. Existing LLM serving systems like Faster Transformer and Orca required pre-allocating contiguous memory chunks based on each request's maximum possible sequence length, typically 2048 tokens, even though most requests used far fewer tokens, resulting in what the researchers measured as 61.8% to 79.6% memory waste across different workloads. To understand the magnitude of this waste, consider that in a 13B parameter model running on an NVIDIA A100 GPU, the KV cache for a single token demands 800 kilobytes of space, calculated from the hidden state size, number of layers, and floating point precision requirements, like a filing cabinet where each document folder requires its own dedicated drawer. With sequences potentially reaching 2048 tokens, a single request could consume up to 1.6 gigabytes of the GPU's 40 gigabyte memory, just for temporary storage, severely limiting how many requests could be processed simultaneously, and ultimately constraining the system's throughput. The Berkeley team's solution drew inspiration from an unexpected source: operating systems virtual memory management, where physical RAM pages don't need to correspond to contiguous virtual addresses, much like how a library's books can be scattered across different shelves while still appearing in logical order in the catalog. They developed paged attention, an attention algorithm that breaks the KV cache into fixed-size blocks that can be stored in non-contiguous memory locations, allowing for dynamic allocation as tokens are generated, rather than pre-reserving massive chunks of memory that mostly sit empty. Paged attention transforms the traditional attention computation by partitioning key and value vectors into blocks, each containing a fixed number of tokens, then performing attention calculations block by block rather than requiring everything to be stored contiguously, like assembling a jigsaw puzzle where pieces can be fetched from different boxes as needed rather than requiring all pieces to be laid out on the table from the start. The mathematical formulation splits the attention computation into block-wise operations, where attention scores are computed between query vectors and key blocks, then combined with corresponding value blocks to produce the final output. Building on paged attention, the researchers created VLLM, a distributed serving engine that manages KV cache memory using virtual memory principles, maintaining block tables that map logical KV blocks to physical memory locations like a sophisticated hotel reservation system, that can assign guests to any available room while maintaining their preferred floor sequence. Each request's KV cache is represented as a series of logical blocks, filled from left to right as new tokens are generated, with the system dynamically allocating physical blocks only when needed, rather than reserving space for the maximum possible length upfront. The memory management system maintains separate logical and physical block spaces, with a block engine on GPU workers dividing memory into fixed-size physical blocks, and a KV block manager tracking the mapping between logical and physical blocks for each request, functioning like a warehouse management system where products can be stored in any available bin while the computer tracks their logical locations. This separation eliminates the need to reserve memory for maximum sequence lengths, dramatically reducing waste, while enabling more requests to fit in memory simultaneously. During decoding, VLLM demonstrates its efficiency through a three-step process that starts with allocating only the necessary blocks for the prompt phase, then dynamically adding blocks as tokens are generated, much like a restaurant that starts customers with basic table settings and brings additional utensils only as each course arrives. For a 7-token prompt, the system maps just 2 logical blocks to available physical blocks, processes the prompt with conventional attention, then uses paged attention for subsequent token generation, while allocating new blocks only when existing ones fill up. The system's true innovation becomes apparent in complex decoding scenarios, like parallel sampling and beam search, where multiple output sequences can share portions of their KV cache, particularly the prompt portion that remains identical across all variants, like multiple photocopies that can share the same original document, rather than requiring separate copies of the source material. In parallel sampling, different sequences from the same prompt share logical blocks for the prompt portion, while maintaining separate blocks for their divergent generation phases, enabling substantial memory savings. Beam search presents an even more sophisticated sharing pattern, as sequences can share KV cache blocks as long as their token histories remain identical, with sharing patterns evolving dynamically as beams diverge, resembling a family tree where relatives share common ancestors but branch into separate lineages over generations. The researchers found that beam search could achieve up to 55% memory savings through this intelligent sharing mechanism, far beyond what traditional contiguous memory allocation could support. To handle the variable and unpredictable lengths of LLM requests, VLLM implements preemptive scheduling that can swap KV cache blocks between GPU and CPU memory when resources become constrained, functioning like a sophisticated air traffic control system that can redirect flights to alternate airports when the primary destination becomes overcrowded. When GPU memory fills up, the system can move some requests' KV blocks to CPU memory, then reload them when GPU space becomes available, ensuring continuous operation even under heavy load. The experimental evaluation revealed dramatic performance improvements across multiple scenarios, with VLLM achieving 2 to 4 times higher throughput compared to existing state-of-the-art systems, while maintaining identical output quality, like upgrading from a single-lane bridge to a 4-lane highway, while ensuring the same vehicles reach their destinations. The researchers tested on popular models, including GPT, OPT, and Llama, with varying sizes, finding that improvements became more pronounced with longer sequences, larger models, and more complex decoding algorithms. In basic sampling scenarios, VLLM consistently outperformed faster Transformer and Orca across different model sizes, with particularly strong gains on the 13B parameter models, where throughput improvements reached 2.2 times for OPT and 3.5 times for Llama. Measurements taken on NVIDIA A100 GPUs with careful attention to maintaining equivalent latency characteristics, like comparing assembly lines where the new design produces significantly more units per hour without sacrificing quality control standards. The performance advantages grew more substantial as sequence lengths increased. validating the researchers' focus on memory efficiency. For parallel sampling workloads, where requests generate multiple output candidates, VLLM's memory sharing capabilities delivered even more impressive results, achieving 3.7 times throughput improvement for certain configurations by effectively sharing the prompt portion of KV cache across all samples while maintaining separate storage for the divergent generated portions, like a printing press that can produce multiple copies from a single typeset rather than requiring separate typesetting for each copy. The system demonstrated particular strength in scenarios common to programming assistants and other applications requiring multiple output options. Beam search evaluation revealed VLLM's sophisticated memory management at its most complex, handling the dynamic sharing patterns as search beams converge and diverge, while maintaining 2.3 times to 3.2 times throughput improvements over traditional systems. Performance that stems from the ability to share KV cache blocks among beams with identical token histories, like multiple explorers following the same path through a maze until they encounter decision points where they must choose different routes. The memory savings from this sharing approach proved substantial, reaching 55% in some configurations. The researchers also validated VLLM's distributed capabilities across multiple GPUs, demonstrating that the page detention algorithm and block-based memory management scale effectively in distributed settings, where model parameters are sharded across devices, each maintaining its own pool of KV blocks, while coordinating through a centralized scheduler, resembling a distributed library system, where different branches hold different sections but share a common catalog and request routing system. The distributed implementation maintained the same memory efficiency benefits while enabling larger models and higher overall throughput. Ablation studies examining the impact of block size revealed an interesting trade-off between memory efficiency and computational performance, with smaller blocks reducing memory fragmentation but potentially increasing kernel overhead, while larger blocks improved computational efficiency at the cost of some memory waste within partially filled blocks, like choosing between small, precisely sized shipping containers that minimize waste but require more handling, versus larger containers that simplify logistics but may carry some empty space. The researchers found that block sizes of 16 tokens provided a good balance for most workloads. The broader implications of this work extend beyond immediate performance improvements. As the memory management challenges addressed by page detention and VLLM are becoming increasingly critical as language models grow larger, while GPU memory capacities scale more slowly, creating a widening gap between computational capability and memory resources, like a growing city where transportation infrastructure struggles to keep pace with expanding residential and commercial development. The researchers noted that from NVIDIA A100 to H100, computational performance increased by more than 2x, while maximum memory remained capped at 80 gigabytes. Looking at the practical deployment considerations, VLLM's open source availability has enabled widespread adoption across the industry, with the system supporting popular model architectures and providing APIs compatible with existing LLM serving frameworks, functioning as a drop-in replacement that immediately improves efficiency without requiring application changes, like upgrading a building's electrical system with more efficient components while keeping all the outlets and switches in the same familiar locations. The codebase includes optimized CUDA kernels for page detention and comprehensive distributed execution support. The work represents a significant advance in the practical deployment of large language models, demonstrating how techniques from classical computer systems can solve modern machine learning challenges, with page detention's virtual memory approach providing a foundation for future innovations in memory-efficient ML serving, much like how early database indexing techniques continue to influence modern data storage systems decades after their initial development. By achieving near-zero waste in KV cache memory management, VLLM has established a new standard for LLM serving efficiency that subsequent systems will need to match or exceed. You've just learned about the elegant solution researchers found to memory management problems that were limiting AI performance, like organizing a more efficient parking system for digital resources. Take a gentle breath and let that sense of problem solving settle with you. The way smart people identify bottlenecks and create better solutions. You don't need to remember the technical details of paged attention. Just feel grateful that such thoughtful optimization is happening behind the scenes. Now, let's journey back to 2020 and meet GPT-3, the model that first showed us how AI could learn new tasks from just a few examples, demonstrating capabilities that seemed almost magical at the time. Back in 2020, researchers at OpenAI published a landmark study that fundamentally shifted how we think about language models and their learning capabilities. Introducing GPT-3, a 175 billion parameter autoregressive language model that demonstrated remarkable few-shot learning abilities without any task-specific training. Like a master craftsman who can adapt their skills to new projects after years of apprenticeship, GPT-3 showed it could perform novel language tasks simply by observing a few examples in its input context, without updating its underlying parameters through traditional fine-tuning processes. The core insight driving this research was that while the prevailing paradigm of pre-training followed by fine-tuning had shown impressive results, it still required thousands or tens of thousands of labeled examples for each new task, creating a significant bottleneck for practical applications. The authors observed that humans can typically learn new language tasks from just a brief instruction or a handful of demonstrations, suggesting that current NLP systems were missing some fundamental capability, and they hypothesized that dramatically scaling up model size might unlock this more flexible form of learning, like a library that becomes more useful as it grows larger, allowing visitors to find increasingly specialized information through browsing rather than formal study. The researchers theorized that larger language models might develop the ability to recognize and adapt to new tasks purely through pattern matching within their parameters. To test this hypothesis, the team trained 8 different model sizes ranging from 125 million to 175 billion parameters, with GPT-3 representing the largest model at 175 billion parameters, making it 10 times larger than any previous non-sparse language model at that time. The architecture closely followed GPT-2, using the same transformer design with modified initialization, pre-normalization, and reversible tokenization, but incorporated alternating dense and locally banded sparse attention patterns across the transformer layers. And all models used a context window of 2048 tokens to accommodate multiple demonstration examples, like a telescope array where each additional mirror captures more distant light. Each increase in model size was designed to capture increasingly subtle patterns in language that could enable more sophisticated few-shot reasoning. The training dataset represented a careful curation of internet text, combining a filtered version of Common Crawl with high-quality reference corpora, including an expanded web text dataset, 2 book collections, and English Wikipedia, totaling approximately 300 billion tokens. Rather than sampling datasets proportionally to their size, the researchers weighted higher quality sources more heavily, accepting some overfitting in exchange for better training data quality, with Common Crawl comprising 60% of the training mix, despite containing the most tokens, while Wikipedia and book collections were sampled multiple times during training, like a chef who carefully balances ingredients not by volume, but by their contribution to flavor. This approach prioritized data quality over simple quantity in constructing the training mixture. The evaluation framework distinguished between 4 different learning settings: traditional fine-tuning with gradient updates on task-specific datasets, few-shot learning with typically 10 to 100 demonstration examples provided in the context, one-shot learning with exactly 1 demonstration plus a natural language task description, and zero-shot learning where only a natural language instruction was provided without any examples. For multiple choice tasks, the model compared the likelihood of different completions given the context. While for free-form generation tasks, beam search was used with specific parameters, including a beam width of 4 and length penalty of 0.6, with performance measured using F1 similarity, BLEU scores, or exact match depending on the dataset. Like a student taking exams under increasingly challenging conditions, from open book with examples to closed book with only verbal instructions, GPT-3 was tested across this spectrum of support levels to understand its adaptation capabilities. The results demonstrated that language modeling performance continued to follow a smooth power law relationship with compute, even when extended by 2 additional orders of magnitude beyond previous studies, suggesting that the fundamental scaling trends observed in earlier work remained valid at unprecedented model sizes. More importantly, the gap between 0-shot, 1-shot, and few-shot performance grew with model size, indicating that larger models were becoming increasingly proficient at meta-learning and in-context adaptation, with the few-shot settings showing the most dramatic improvements as parameters increased. Like a musician whose ability to improvise grows more sophisticated with experience, allowing them to pick up new styles more quickly, larger language models showed enhanced capacity for recognizing and adapting to new patterns from minimal examples. On traditional language modeling tasks, GPT-3 achieved a new state-of-the-art perplexity of 20.50 on PenTreeBank, representing a substantial 15-point improvement over previous results. While on the Lambda dataset, which tests long-range dependency modeling, GPT-3 achieved 76% accuracy in 0-shot settings and reached 86.4% in few-shot settings by reformatting the task as a fill-in-the-blank exercise. The few-shot approach proved particularly powerful for Lambda because it allowed the model to understand that exactly one word was required for completion, rather than treating it as an open-ended continuation task, demonstrating how task framing could significantly impact performance. Like a key that works better when you understand how to turn it, the same underlying capabilities could be unlocked more effectively through appropriate task presentation. For closed book question answering, where models must rely entirely on knowledge stored in their parameters rather than external references, GPT-3 showed substantial improvements with scale and context, achieving 71.2% on Trivia QA in the few-shot setting, compared to 64.3% in 0-shot, with this few-shot performance matching the state-of-the-art achieved by fine-tuned models operating in the same closed-book setting. On natural questions, GPT-3 reached 29.9% accuracy in few-shot settings, and on web questions, it achieved 41.5%, both representing significant improvements over 0-shot performance, though still trailing the best fine-tuned systems that could achieve over 40% and 45%, respectively, on these challenging datasets. Like a scholar who can recall more relevant information when given contextual hints about the type of knowledge needed, GPT-3's factual recall improved markedly when provided with examples of the expected response format. Translation capabilities emerged particularly strongly in few-shot settings, with GPT-3 demonstrating competence across multiple language pairs despite not being explicitly trained as a translation system, showing that the model had absorbed multilingual patterns from its diverse training data and could apply them when prompted with appropriate examples. The model also showed proficiency on Winograd schema-like tasks, which require common-sense reasoning to resolve ambiguous pronouns, and performed well on various reading comprehension benchmarks, though it struggled more with some natural language inference tasks and certain reading comprehension datasets, like race. Like a polyglot who discovers they can navigate a new language by drawing on similarities with familiar ones, GPT-3 leveraged its broad linguistic exposure to tackle tasks it had never been specifically trained to perform. On Superglue, a challenging benchmark suite designed to test advanced language understanding, GPT-3's few-shot performance approached but did not consistently exceed fine-tuned baselines, achieving strong results on some subtasks while showing clear limitations on others, particularly those requiring complex logical reasoning or handling adversarially constructed examples. The model demonstrated impressive performance on synthetic tasks designed specifically to test few-shot learning, including arithmetic operations, word unscrambling, and using novel words and sentences after seeing them defined only once, suggesting that the few-shot learning capability extended beyond just pattern matching to include genuine on-the-fly reasoning, like a Swiss Army knife that proves surprisingly versatile but still has limitations compared to specialized tools. GPT-3 showed broad competence across many tasks, while revealing specific areas where targeted training remained superior. Perhaps most remarkably, GPT-3 demonstrated the ability to generate synthetic news articles that human evaluators found difficult to distinguish from human-written content, raising important questions about potential misuse and the need for detection mechanisms, while also highlighting the model's sophisticated understanding of textual structure and content generation capabilities. The researchers conducted systematic studies of data contamination, developing tools to measure whether test set content had inadvertently appeared in the training data, and found that while contamination had minimal effect on most datasets, a few showed potential inflation of results, leading them to mark affected evaluations with asterisks or exclude them entirely. Like a detective carefully examining evidence for contamination, the team worked to ensure their remarkable results reflected genuine capabilities rather than memorization artifacts. The study also revealed important limitations that would prove prescient for future development, including struggles with certain natural language inference tasks, inconsistent performance on some reading comprehension datasets, and challenges with tasks requiring precise logical reasoning or mathematical computation beyond simple arithmetic. The authors noted that while few-shot performance often approached fine-tuned baselines, it rarely exceeded them consistently, suggesting that task-specific optimization still provided meaningful advantages for many applications, and they acknowledged concerns about bias, fairness, and broader societal impacts that would require ongoing attention. Like a powerful engine that still requires careful tuning and safety measures, GPT-3's capabilities came with both tremendous potential and significant responsibilities for the research community. The energy consumption and computational requirements for training GPT-3 represented a substantial investment, requiring sophisticated distributed training across multiple GPUs and careful optimization of batch sizes and learning rates scaled appropriately for each model size, with the largest model taking significantly more compute than previous language models while still following the established scaling laws for efficiency. The training process involved careful hyperparameter selection, with larger models using proportionally larger batch sizes but smaller learning rates, and the team employed gradient noise scaling to guide these choices, training all models for exactly 300 billion tokens to ensure fair comparison across different sizes, like building a cathedral that requires both massive resources and precise engineering. Creating GPT-3 demanded both unprecedented computational scale and careful attention to training dynamics. Looking back from our current vantage point in 2026, this 2020 paper proved to be a watershed moment that established few-shot learning as a fundamental capability of large language models and demonstrated that scaling could unlock qualitatively new behaviors rather than just incremental improvements. The work showed that the smooth scaling laws observed in smaller models continue to hold at much larger scales, providing confidence for subsequent scaling efforts that would follow in the years after publication, and introduced evaluation frameworks and methodological considerations that became standard practice for assessing large language models. Like a map that reveals new territories for exploration, GPT-3 opened up research directions that continue to influence the field today, from investigations into emergent capabilities to studies of in-context learning mechanisms. The broader implications of this work
extended far beyond technical achievements, raising questions about the nature of intelligence, learning, and the potential for artificial systems to demonstrate human-like adaptability without explicit programming for specific tasks, while also highlighting the need for careful consideration of deployment risks and societal impacts as these systems became more capable. The demonstration that language models could perform novel tasks through pattern recognition and in-context learning, rather than requiring task-specific fine-tuning, suggested new possibilities for more general artificial intelligence systems, while also emphasizing the importance of responsible development and deployment practices. Like a door opening onto an unexplored landscape, this research revealed both exciting possibilities and important challenges that continue to shape how we think about artificial intelligence and its role in society. You've just witnessed GPT-3's remarkable ability to learn new tasks from just a handful of examples, like a craftsman adapting their skills to new projects with graceful ease. Let that image of flexible learning rest peacefully in your thoughts. The beauty of a system that could understand and adapt so readily. There's no need to hold on to the specifics of parameter counts or training details, just the wonder of that leap forward in AI capability. Now, as we near the end of our journey, let's explore how researchers took these powerful but sometimes wayward systems and taught them to be truly helpful, creating the foundation for the personal agents that can work so thoughtfully alongside us today. Back in 2022, OpenAI's research team tackled one of the most fundamental challenges in artificial intelligence alignment: the gap between making language models bigger and making them actually helpful to users. Like a powerful race car that lacks steering, large language models such as GPT-3 could generate impressively fluent text, but often veered into unhelpful territory, producing outputs that were untruthful, toxic, or simply failed to follow the user's instructions, despite their massive scale and computational sophistication. The researchers developed a 3-step training methodology that functioned like a careful apprenticeship program, beginning with human demonstrators showing the model exactly how to respond to various prompts through supervised learning. In the first phase, they collected approximately 13,000 training examples where human labelers wrote ideal responses to prompts, then fine-tuned GPT-3 to mimic these demonstrations, creating what they called supervised fine-tuning models, or SFT. The second phase operated like a judging panel at a competition, where human evaluators compared multiple model outputs and ranked them according to quality and helpfulness. The team collected 33,000 comparison examples, using this preference data to train a separate reward model that could predict which responses humans would prefer, essentially creating an automated critic that learned to evaluate outputs the way humans would. The final training phase resembled a feedback loop between student and teacher, using reinforcement learning with the proximal policy optimization algorithm to fine-tune the supervised model based on rewards from the trained reward model. This process, called reinforcement learning from human feedback, or RLHF, continuously improved the model's ability to generate responses that aligned with human preferences, resulting in what they named Instruct GPT. The results proved remarkable, like a lightweight boxer defeating a heavyweight champion through superior technique rather than raw power. Despite having 100 times fewer parameters, the 1.3 billion parameter Instruct GPT model consistently outperformed the 175 billion parameter GPT-3 in human evaluations, with labelers preferring Instruct GPT outputs 85% of the time over standard GPT-3 responses, and 71% of the time even when GPT-3 was given few-shot prompting to improve its instruction following ability. On truthfulness metrics, Instruct GPT demonstrated improvements that resembled the difference between a reliable witness and an unreliable narrator. Using the Truthful QA benchmark, Instruct GPT generated truthful and informative answers about twice as often as GPT-3,
While on closed-domain tasks like summarization, the model hallucinated information not present in the input only 21% of the time, compared to GPT-3's 41% hallucination rate. The toxicity evaluations revealed more modest improvements, like a small but meaningful reduction in harmful speech patterns. Using the real toxicity prompts dataset, InstructGPT generated approximately 25% fewer toxic outputs than GPT-3 when explicitly prompted to be respectful, though the researchers found no significant improvements on bias measures using the Winogender and Krulles pairs datasets. An interesting challenge emerged during training, resembling the trade-offs in specialized education, where focusing on one skill can temporarily weaken others. The RLHF fine-tuning process caused performance regressions on some public NLP datasets, including Squad, Drop, HelloSwag, and WMT translation tasks, what the researchers termed an alignment tax for the improved instruction-following behavior. To address these regressions, the team developed a hybrid approach that functions like a balanced diet, mixing the specialized RLHF training with updates that maintained connection to the original pre-training data distribution. This modified technique, called PPO-PTX, largely eliminated the performance drops on public datasets while preserving the gains in human preference scores. The researchers conducted generalization experiments that worked like testing a student's ability to apply learned principles to new situations they had never seen before. They found that InstructGPT could follow instructions for summarizing code, answering questions about programming, and even responding to instructions in different languages, despite these types of prompts being very rare in the fine-tuning data. However, the limitations remain significant, like persistent blind spots in an otherwise improved system. InstructGPT still made simple mistakes, failing to follow some instructions, fabricating facts, giving unnecessarily hedged responses to straightforward questions, or failing to detect when instructions contained false premises. The team hired approximately 40 contractors through Upwork and Scale AI to serve as human evaluators, implementing a screening process that functioned like auditions for a specialized role requiring sensitivity to potential harms and demographic considerations. Inter-annotator agreement reached 72.6% among training labelers and 77.3% among held-out labelers, indicating reasonably consistent human judgment despite the complexity of the evaluation task. When compared to models trained on public instruction-following datasets like FLAN and T0, InstructGPT demonstrated superior performance that resembled the advantage of custom tailoring over off-the-rack clothing. On their API prompt distribution, InstructGPT achieved a 73.4% win rate against their supervised baseline, while FLAN and T0 variants achieved only 26.8% and 29.8% win rates respectively. The research methodology built extensively on prior work in reinforcement learning from human feedback, originally developed for simple robotic tasks and Atari games, but more recently applied to text summarization by teams like Ziegler and colleagues in 2019 and Steinen and colleagues in 2020, representing a natural evolution like the progression from basic tools to sophisticated instruments. The dataset composition revealed the practical nature of real API usage, resembling a busy restaurant's diverse menu, rather than the standardized offerings of academic benchmarks. Most prompts involve generative tasks rather than classification or question answering, with users requesting everything from creative writing to business communications, with over 96% of prompts written in English. The team acknowledged important limitations regarding alignment targets, noting that their approach aligned models to the preferences of their specific group of labelers and researchers rather than to any universal notion of human values, like tuning an instrument to one particular concert hall
rather than achieving perfect acoustics everywhere. The broader implications of this work proved significant for the field of AI alignment, demonstrating that human feedback could effectively modify large language model behavior across diverse tasks, though substantial challenges remained in scaling these approaches and ensuring robust generalization beyond the training distribution, like establishing a promising foundation that still required extensive construction work. And here we rest at the end of our gentle journey, having traced the path from distant cloud services to the personal AI agents that are coming to live quietly on our own devices. You've seen how researchers have tackled challenge after challenge, from making these systems efficient enough to run locally, to teaching them to be helpful and aligned with what we actually need. The open source agents blooming across GitHub, the RTX PCs designed to host them, the careful work to make them both powerful and private. All of this represents a homecoming of sorts for artificial intelligence. As you drift towards sleep, you can rest knowing that the future of AI assistance is becoming more personal, more private, and more aligned with the rhythms of your own life. Sweet dreams, dear friend, and may your rest be peaceful and deep.